Hey gang, I'm feeling particularly rosy today. You know why? It's color day. Well, it's the first of 2 color days. Last time, we talked about how we go from light outside the eye to action potentials in the optic nerve. So in the simplest possible scenario, you're in a fully pitch black room and there's a tiny, tiny point of light. That single point of light activates some particular patch of photoreceptors in the retina, and those signals are then carried up to the brain. So that's the simple scenario. But look around the room that you're in right now. You're seeing much more than simple flashes of light. So today we'll start talking about how we go beyond detecting the mere presence of light and talking about how we differentiate between different colors. So we'll start with an overview of what color is, then we'll talk about how color is transduced and coded in the brain, and next time we'll do more on top-down effects and how our expectations affect color perception. The study of color goes back literally hundreds of years. So Isaac Newton in the early 1700s shone sunlight through a prism and revealed a rainbow on the other side. This occurred because different wavelengths refract at different angles. So when you shine white light through a prism, you reveal all of the colors that are contained within because those wavelengths of light bend differently from one another. Here's what it looks like in Lego form. So this means, this demonstration showed that white light, what comes off of the sun, what comes out of most light bulbs, contains all wavelengths of light. Not necessarily equally, we'll talk more about that next time. So what we're going to start by doing is trying to come up with a working definition of what color is. This turns out to be a very difficult thing to do. So intuitively, you might say, based on what you read, that color is a property of light. Right? We talked about the fact that certain wavelengths are associated with certain colors. So maybe color is just the wavelengths of light that are present. And objects have different colors because they reflect some wavelengths and absorb others. So when white light that contains all wavelengths of light is shown on a red apple, that apple looks red because it's absorbing everything except the long wavelengths. So the long wavelengths are reflected back to us and appear red. So maybe we could say that red is things that reflect about 670 nanometer light, right? That the color that an object appears to be is a function of the wavelengths of light that it reflects. But there's something a little bit wrong with this. It can't be all about the wavelengths that are present, because we cannot, for instance, distinguish between 580 nanometer pure light. So you could think of this like a pure tone, like a single wavelength. We can't distinguish between that and the simultaneous presence of 540 nanometer light and 620 nanometer light. Those both appear yellow to us. So the reading introduced you to the term metamer. These are 2 physically different stimuli that we perceive as being identical. Jason Decker in the philosophy department refers to these as true yellow, that's the 580 nanometer light, and fool's yellow, the combined red and green together. And the fact is, anytime you look at a yellow object, look around the room, see if you can find a yellow object. You don't know if that's reflecting 580 nanometer light or if it's reflecting the combination of 540 and 620 nanometer light. So you don't know when you see yellow if it's true yellow or fool's yellow. It looks the same even though it's made out of different wavelengths. So in fact, if we were to try to define yellow by the wavelengths of light that are present, this is not yellow. It looks yellow, right? But the digital device that you're watching this on likely is not capable of producing 580 nanometer light. So computers, projectors, phones, they're only capable of producing red, green, and blue light. So if you were to zoom in enough that you could see the individual pixels on your screen, it would look like the red and green lights you see at the bottom of the screen. You can prove this for yourself by opening the color tools on your computer. You can do this in PowerPoint or in Google Sheets and adjust the color of a particular object by moving these sliders around. So to make yellow here, I've turned up red and green all the way and turned down blue. You still don't believe me? Okay, let me try to prove it to you. This is a magnifying lens that fits over the lens of the camera on my iPhone. If I zoom in on something as far zoomed in as it can go and have the 15 zoomed lens on, it's possible to see individual pixels on this yellow portion of the computer screen. And what do we see? It's red and green. Here's further proof. You see the yellow in the middle panel there? Okay, if we cut out everything else, so we're just looking at a slice of that pure yellow, and we zoom in on it, get your face close to the screen, gang, it's just red and green. So our definition of color certainly can't be about the wavelengths of light that are present, because that would make this not be yellow. And that looks very yellow to me. So we can't say that color is just a property of light or the wavelengths that an object represents, because different kinds of light and different kinds of reflectance produce the same perceptual experience. So we say, okay, so we have to incorporate something about the actual experience of perceiving color. It can't just be something about the stimuli. So what if we say that color is a sensation? The neural code that we get for true yellow, that is 580 nanometer light, is the same as the neural code we get for fool's yellow, that's a combination of 540 and 620 nanometer light. So maybe we could say that color is defined by the pattern of neural activity that these different stimuli produce. But that still doesn't quite work either. Here's why. Check this out. Are any of these circles yellow? This is not a trick. No, they're not. They just don't look yellow, right? Okay. How about this one? What color do the bananas appear? They look yellow, right? I mean, yeah, there's clearly like a pink filter on them, but you can tell those bananas are yellow, right? That's giving you a perceptual experience of yellow. But if we use the eyedropper tool to select particular regions anywhere within the picture, what you see is that none of those individual locations on the banana that look really yellow in the banana picture actually look yellow in isolation. So there's no true yellow in this picture, clearly, because your computer can't produce true yellow. But there isn't even actually any fool's yellow. There's no yellow in that picture. So there are no wavelengths associated with yellow light, and your photoreceptors are not sending signals up to your brain that are associated with yellow light. So the yellow that you see is not coming from the image, and it's not coming from your photoreceptors. That's being generated at a higher level in your brain. So we can't say that color is even a sensation. It can't even be purely about neural code. So what is color? I mentioned that people have been studying color for a long time. Here's a great quote from over 200 years ago that really speaks nicely to this question. In ordinary life, we call white not what looks white, but what would look white if it were set out in pure sunlight or light whose quality did not differ much from sunlight. It is more the potential to be white and become white in all its gradations that we call white in some object, rather than the pure white color itself. So when we talk about color, we're talking about like its potential to be that color. You can tell that those bananas should be yellow and they're just behind a red filter. So if we take a red apple outside in bright sunlight and we bring it inside where it's a little bit dimmer and the quality of the light is different because of the light bulbs we're using, or if I shine a purple flashlight on it, the true essence of the color of that object hasn't changed. So what this quote is arguing is that what color is our ability to discern the true nature of that object despite changes in illumination. So the working definition of color that we're going to use in this course is that color is a perceptual experience. It's not just about wavelengths. It's not just about neural code. It's about a perceptual experience that we have that depends in part on the wavelengths of light that an object reflects and the wavelengths of light that are present. So the quality of the illumination. But our experience also depends on colors that are nearby or things we have recently viewed. More about that next time. And our experience of color depends on the expectations we have about what color they should appear to us. So let's start with the wavelengths of light that an object tends to reflect. As you read, we can quantify the amount of light reflected and absorbed using reflectance curves. So here, the percentage of light that's reflected is along the y-axis, and the wavelength of the whole visible spectrum is along the x-axis. So let's look first at white paper. So white paper is reflecting all wavelengths of light pretty equally, meaning that light bouncing off of white paper contains wavelengths associated with all colors. White objects reflect all wavelengths of light. The tomato, in contrast, is absorbing wavelengths that are below about 540 nanometers and reflecting all of those that have longer wavelengths. So in shorthand, we sometimes refer to short, medium, and long wavelengths of light, with short being the bluish ones, medium being the greenish yellow ones, and long being the kind of orangish reddish ones. So we're going to talk about 3 psychological dimensions of color that are all related to their spectral properties. So the first way that colors can differ from one another is in hue. And hue is what we typically think of as color. It's determined by the wavelengths that are present. So as you move around the wheel that you see here, what is changing is the hue. So the thing that bright orange and bright blue differ on is their hue. So the objects that create the 2 reflectance curves that you see here differ only in hue. We call the one on the left blue and the one on the right orange. So in the schematic that I just showed, this means that the object on the left, the blue object, is reflecting a really narrow band of wavelengths from about 400 nanometers to about 450 nanometers, and it's absorbing the rest. So hue is our first dimension. Our second dimension on which colors can differ is saturation. Saturation refers to the purity of the light. So we talk about colors in terms of being pastel or deep or rich. That's all about saturation. Colors that are highly saturated reflect just a narrow spectral band. So in this one here, you can see that it's reflecting wavelengths that are just around 500 nanometers, but nothing above that or below that. As colors get more unsaturated, they start reflecting a wider spectral range. So the 2 curves that are shown there have the same hue because they're centered on the same wavelength, but they differ in saturation because they differ in the selectivity with which they are reflecting that one wavelength versus kind of a range of wavelengths around them. So if you look at a white piece of paper, that's very highly unsaturated because it's reflecting all wavelengths at once. Gray and black paper are also highly unsaturated because they're also reflecting all of the wavelengths at once. So white, gray, and black are the most kind of fair of colors because they're treating all of the wavelengths equally. They're just reflecting all of them. When you're painting, one of the things that differentiates better paints from worse paints, why some paints are more expensive, is in part because better paints are more highly saturated. It's really hard to get chemicals that reflect only a narrow band of wavelengths, and so cheaper paints are more unsaturated and reflect more wavelengths. So if black, white, and gray are all reflecting all wavelengths, what differentiates them is brightness. So brightness has to do with the amount of light that's being reflected. So we represent this as the height of the spectral distribution. So when we talk about things being dark or bright, we're talking about brightness. So black, white, and gray are all totally unsaturated, but they differ in brightness. So white light is very bright, meaning white objects are reflecting lots of light, whereas gray are reflecting less, and black is basically absorbing everything. I find this schematic to be really helpful. Hue is what changes as you move around the outside of the circle. Saturation is what changes as you go from the inside to the outside. And brightness is what changes as you go from black to bright red in this case. So you can create any color simply by moving these 3 dials around. So any color that you see, we can represent just using hue, saturation, and brightness. All right, so we've now established the nature of the stimulus. Things that we perceive as different colors differ in hue, saturation, and brightness. And we talked last time about how we go from photons to neural code. The next question is, how does the brain interpret particular patterns of action potentials as being associated with specific colors? So the reading gave you a little introduction to trichromatic theory, which describes the fact that there are 3 different types of cones in the retina that are each maximally sensitive to different wavelengths of light. So we have cones that we refer to as short wavelength sensitive, medium wavelength sensitive, and long wavelength sensitive cones. Sometimes we just call them short, medium, and long cones. That doesn't refer to the size of the cone, it refers to the nature of the light that they're sensitive to. So the reason that different cones are sensitive to different wavelengths of light has to do with the characteristics of the photopigment that they contain. So the retinol in each cone is sensitive to different wavelengths of light. So if short wavelength light, what we would perceive as blue, if that hit the retinol in a long wavelength sensitive cone, it wouldn't cause the retinol to isomerize. So it wouldn't lead to the electrochemical cascade that would ultimately change the firing rates of the retinal ganglion cells. So each particular type of cone is sensitive to a specific range of frequencies. But it isn't all or none. The photopigment within the cones are maximally sensitive to particular wavelengths, but they may also be somewhat sensitive to nearby wavelengths as well. So this graph shows the relative sensitivity of short sensitive cones, shown in blue, medium sensitive cones, shown in green, and long wavelength sensitive cones, shown in red. So a short wavelength sensitive cone is the most sensitive to about 440 nanometers wavelength light, but will also respond to slightly longer or shorter wavelengths. Students in the past have said that it's useful to think of these as reflecting activity or stimulation of the cones as well. It isn't accurate to say that these represent the firing rates in the cones, but you can think of these curves as the amount that the response of each type of cone changes when presented with each wavelength of light. So our ability to distinguish between different wavelengths depends on the relative activity in these three different types of cones, each having a unique spectral sensitivity. So each particular wavelength of light produces a unique pattern of activity in the three cones. If we were to present this short wavelength light at about 440 nanometers, that would cause a lot of change in the activity in short wavelength sensitive cones, and a bit of activity in the medium cones, and hardly any in the long cones. So perceived color is based on the relative amount of activity, the pattern of activity in the three types of cones. And what's really remarkable is that any color can be made with combinations of these primary cone colors, because every wavelength from 400 to 700 nanometers produces a unique combination of responses by the three types. So let me just say that again. Every point on the visible spectrum produces a different pattern of activity in the three cones. So with just three values, how much stimulation of short and medium and long wavelength cone, how much activity there is, we can represent the full visible spectrum. But it takes all three cone types to do that. If you're missing one type of cone, your perceptual world looks very different. So color deficiency or color blindness is most commonly caused by missing either the long or medium wavelength sensitive cones. So rather than having trichromatic, tri-3 color vision, these people are called dichromats, di-2, because they have only the short wavelength sensitive cones and either the mediums or the longs, but not both. And so this leads to a lot of difficulty distinguishing between those wavelengths that the medium and long wavelength sensitive cones are responsible for distinguishing. So, for example, in one kind of dichromacy, deuteranopia, this is caused by missing the medium wavelength sensitive cones. Deuteranopia affects about 1% of males and 0.01% of females. And so someone with deuteranopia would see this image as looking more like this. So notice what happens if we remove the medium wavelength sensitive cones, if the person just didn't have those. Now, when 550 nanometer light is presented, that would be coded as no response from the short cones and a moderate change in response from the long cones. When 600 nanometer light is presented, that will also be coded as no response from the short cones and a moderately high response from the long cones. So if the brain is getting the exact same neural code for the two stimuli, it can't distinguish between them. So red and green look the same. The common way that people test for color blindness is using what are called Ishihara plates. So the full color image is shown on the left, and on the right is what simulated color blindness for someone with deuteranopia would see. So people with typical color processing can easily see the 3 in the field of red and orange and yellow dots. People with deuteranopia aren't able to pick out the 3 because they can't use the difference in color to distinguish the figure, the 3, from the ground, the dots. There are also what are called reverse Ishihara plates, in which people who are colorblind have an easier time reading the number or letter. So this is a reverse Ishihara plate. If you have typical color vision, you probably can't determine what it says, or it's probably very hard to pick out the letters. But to someone who is red-green colorblind, to someone who has deuteranopia, it looks like this. It spells no. So if you don't have access to the color cues, you can group by brightness instead. So the whites and the grays look more different. Color blindness is somewhat common, including all types. About 8% of males and 0.5% of females have some form of color blindness. The sex difference occurs because the genes that code for long and medium wavelength sensitive cones are on the X chromosome. So if anything is atypical with men's only copy of the X chromosome, it means they're colorblind. If anything is atypical with one of women's, the functional other X chromosome overcomes it. So a person who has 2 X chromosomes can only be colorblind if both of her parents are. So given that colorblindness is relatively common, it's a good idea to avoid making red-green contrasts when creating visualizations. So for example, people with deuteranopia couldn't tell which stores have iPhones or where there is traffic. I once team taught Intro Psych with Neil Lutsky, who is colorblind, and I asked him if it was okay when I was doing lectures in Intro Psych about colorblindness, you know, if I used him as an example. And so when I was talking about having visualizations that are unkind to the colorblind, I put up a schematic of like a Google Maps, and I was like, hey Neil, where is there traffic? And he was like, what are you talking about? And didn't even know that Google represented traffic using different colors. So this is an important source of information that people who don't have access to the red-green distinction just aren't able to see. Luckily, given that the transformations between typical color and dichromacy are pretty straightforward, there are lots of tools available for making websites and charts to assess how materials would look with someone with color blindness. So at some point in your life, you're going to make a chart or a website or convey information in some way that involves color. Given that it's very easy to do that in a way that's widely accessible, I'd encourage you to be kind to the hundreds of millions of people who have red-green color blindness and not use red and green as a distinction that conveys information. Okay, so now we have covered the first 2 components of the perceptual experience of color. Next time, we're going to talk about how things other than the wavelengths of light that are present affect our perception of color. And now, I'm feeling kind of blue to leave you. This is a fun question, right? It's a nice metaphor. So both white light and complex musical notes contain multiple frequencies or wavelengths, right? They are made of multiple components. And both a prism and the basilar membrane split those complex stimuli up into their component frequencies, wavelengths. All right, so if it's bright and saturated, you know it's going to be a narrow curve that is tall. Blue is going to be down at the short wavelength end of the spectrum. Dark grayish green is going to be unsaturated because it's grayish. If it means green, it's going to be centered on those medium wavelengths. And the fact that it's dark means that the reflectance curve is relatively low. It's not reflecting a lot of light. But where's magenta? Where's magenta on the spectrum? It's nowhere. You can only achieve magenta with simultaneous high levels of both short and long wavelength light. Magenta is actually really special in this regard. It's what is called a non-spectral hue. So everything from about 400 nanometers to 750 nanometers takes us from like violetish blue through red. But this color in between red and blue isn't part of that spectrum. So violet is the tone. So violet is the shade that is just on the other side of blue heading toward purple, but magenta is this bright pink that is neither purple nor red. So magenta is actually really, really special. It is only formed by the combination of simultaneous short and long wavelength light. Unlike yellow, light blue, etc., that can be formed in multiple ways, right? There's true yellow and there's fool's yellow. Magenta can only occur in one way. There is no true magenta. There's only fool's magenta. There's no single wavelength associated with it, as there is for all other hues. So if we look at some object that is magenta in the real world, you see that the way that that's achieved is by reflecting light at both short wavelengths and long wavelengths. Magenta! It's really special. So magenta is relatively rare in nature, and it's difficult to manufacture as well because it's hard to get chemicals that selectively reflect long and short wavelength light without reflecting the medium wavelength light in the middle. You're so special. Do you know how special you are? No, you are. But do you know why you're special? Let me tell you. All right, so we talked about blue earlier. Yellow is coded as the highest level of stimulation or the highest change in activity of medium wavelength sensitive cones, moderately high for long wavelength sensitive cones, and little to none from the shorties. Green is similar, but somewhat lower levels of medium and long and higher levels of short. There's red. Okay, so what about white? Well, recall that white is the combination of all wavelengths of light simultaneously. So all cone types respond to white light. So how do we know what colors are present? It is our old friend population coding. If we were to record from just one neuron or one type of neuron, we couldn't tell the difference between yellow and white or really any other color pairs. It's only by looking at the combined responses of all of the cone types that we can know the quality of the light. So like the gustatory system, we're using population coding, but unlike the gustatory system, we can code for many more qualities than we have receptor types, right? In taste, we have 5 receptor types, we can code for 5 things. In color, we have 3 receptor types, and we can code for millions of colors. So in that way, it's somewhat more like the olfactory system, in which we can detect many more odorants than we have types of olfactory receptor neurons. Here's what I'll leave you with today. It's the Queen of England as the spectrum of visible light. See you in class.